Hello students, good time to all. I am Chandan Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss three magnetic vectors, that is B vector, S vector and M vector, their relations and the concept of magnetic susceptibility and magnetic permeability. Let's begin. First, magnetic induction B vector. Whenever a magnetic substance is placed in an external magnetic field, then that substance gets magnetized, and the phenomenon of inducing an induced magnetism in a magnetic substance when placed in a magnetizing field is referred as magnetic induction. Look here, there will be a uniform magnetic field. Let a magnetic substance is placed in between that uniform magnetic field, then that magnetic substance get magnetized. Here the magnetic lines of force are passes throughout that magnet. And that substance becomes a magnet with south pole on left and north pole on the right hand side. In other words, we can say the end into which field lines are entering becomes south pole, and other end from which field lines coming out becomes north pole. Thus, the term magnetic induction is defined as the number of magnetic lines crossing per unit area normally through that of magnetic substance is known as magnetic induction, and that one is denoted by B vector. That magnetic induction is further named as magnetic flux density, or that can also be known as magnetic field. And the SI unit of magnetic induction is Tesla, and CGS unit of magnetic induction is Gauss. Here 1 Tesla is equal to 10 to the power 4 Gauss. Another magnetic vector, that is magnetic intensity, denoted by S vector, which is defined as the degree to which a magnetic field can magnetize a substance. The degree to which a magnetic field can magnetize a substance. Here we take an example of toroidal solenoid. Let there will be the coils. I amount of current entering, I amount of current exist. That one is the toroidal solenoid. Here small n tons per unit length. I amount of current passes through that of toroidal solenoid. So, magnetic field induction, here magnetic field induction of that toroidal solenoid B is equal to mu naught Ni. Mu naught is the permeability of free space, or we can say that is the absolute permeability of free space. Here the product of Ni is known as, here N into I is known as magnetic intensity, that is H, that is magnetic intensity. Now therefore B vector is equal to mu naught, in place of Ni we substitute S vector. So we can easily define magnetic intensity as, here we can define magnetic intensity S vector is defined as the number of ampere turns, the number of ampere turns means Ni, I be the current, N be the number of turns per unit length. So the number of ampere turns flowing round unit length of toroidal solenoid to produce the magnetic induction B in the solenoid, In this way we define magnetic intensity S vector. Okay. Next one, third magnetic vector, that is magnetization vector M vector. Magnetization vector M Look here, when a substance is placed in a uniform magnetic field, it gets magnetized and attains a magnetic dipole moment, and that direction of the magnetic dipole moment is same as that of direction of applied magnetic field, and that magnetic dipole moment is the product of pole strength into length of that magnet. So, here we define the magnetization vector M as the magnetic dipole moment developed for unit volume of that of substance when that is subjected to a uniform magnetic field is known as magnetization vector M, or we can say intensity of magnetization. Intensity of magnetization. So, how we define that one? M is equal to magnetic dipole moment Pm divided by volume. Here Pm is equal to pole strength into length, which is known as magnetic dipole moment. Dipole moment. M is the pole strength of that magnet, L be the length of the dipole, length of the dipole, or M is equal to ml divided by, in case of volume, therefore V volume of the magnet, which is equal to area into length, where A be the area of that magnet. Put it that value here, A into L, so LL cancel out. Magnetization vector M is equal to M divided by A. So, we can define it in another way, that is the magnetization vector M can also be defined as the pole strength per unit area, the pole strength per unit area developed in the material when that is subjected to a uniform magnetic field, when it is placed, or we can say it is subjected to a uniform magnetic field. Uniform magnetic field. And the physical significance of that magnetization vector, that implies the extent to which a substance can be magnetized when that is placed in an external uniform magnetic field. Okay. So, in this way we define three magnetic vectors. One is magnetic induction, another one magnetic intensity, and last one that is magnetization vector. Now, we studied the concept of magnetic susceptibility and permeability. look here, under ordinary conditions the magnetic dipole moments of electron of a magnetic material are oriented randomly, so that the net magnetic dipole moment per unit volume here is 0. But if the substance is placed in case of magnetic field, that is S vector of a solenoid, then the magnetization vector M is developed in that of particular substance. So, experimentally it is found that magnetization vector or intensity of magnetization is directly proportional to that of magnetic field S vector. Okay. Now, we can equalize that one by introducing a proportionality constant. Here M is equal to xi h. Here xi is known as the volume susceptibility of that particular substance, and which is known as the magnetic susceptibility. That is, magnetic susceptibility determines how easily a substance can be magnetized. If we take an example, in case of iron and copper, we say iron has got more susceptibility than copper. What exactly that meaning? That means iron can be magnetized more easily than that of copper. Therefore, the magnetic susceptibility can be defined as, mathematically we can say, magnetic susceptibility is the ratio of the magnetization vector to the magnetic intensity. That is, xi is equal to m by h. That is magnetic susceptibility. Now, magnetic permeability magnetic permeability is defined as the ratio of magnetic induction B vector to magnetic intensity H vector. That is, magnetic permeability, which is written as mu, is equal to B by H. Again, a term is defined, that one is relative permeability. In electrostatics, we introduce a term dielectric constant. Here in magnetostatics, relative permeability play that same role as dielectric constant play in case of electrostatics. So, relative permeability is the ratio, that is the ratio between permeability of a given material, permeability of given material to that of vacuum, to that of vacuum is called relative permeability. Relative permeability, that is mu r, relative permeability is equal to permeability of that of medium to that of permeability of free space, means vacuum. What exactly that permeability refers, means what be the physical significance of that permeability of a substance or medium? That is the ability to allow, or we can say the ability to permit the passage of magnetic field lines through that particular substance. In other words, we can say the extent to which magnetic field can penetrate to that medium, the extent to which magnetic field can penetrate to that medium is called permeability of that particular medium. With the help of that term, we can easily idealize how the magnetic field can penetrate to that of medium. Okay. Now we can relate the relationship between the three magnetic vectors B, S and M. Look here, if in case of paramagnetic materials, exactly what happened in case of paramagnetic material used in case of toroidal solenoid. If we take toroidal solenoid here, the M vector and S vector are in the same direction, and the magnetic effects of that atomic dipoles will reinforce the magnetic induction B vector in that of a toroidal. As you take toroidal here, in that case of a toroidal, the total induction inside that of toroidal is due to the net current I and the magnetization vector M of that particular material. So, here we write that is the experimental factor, we get that from experiments. So, the total induction inside the toroid is due to the net current I be the net current that pass through the toroid, and the magnetization M of that particular material, the material at which the toroid is made. Then the current due to the magnetization, the current due to magnetization is equal to I of M, current due to magnetization, and produces the magnetization M here. Therefore, M, that is the magnetization vector M, is N into Im, N be the number of turns per unit length, that is number of turns per unit length, that current due to the magnetization is Im. So, the magnetization M is equal to N into Im. Here Im is an atomic current that gives rise to the magnetization M of that particular material. That current due to magnetization is Im, that is also is the atomic current, that is an atomic current that gives to the magnetization M of that of material. So, the total current is the sum of true current and the current due to magnetization. Therefore, the total current that is I total is the sum of the true current I and current due to magnetization and magnetization current Im. Okay. Here I total is equal to I true current plus current due to magnetization Im. Therefore, the total magnetic induction in the toroid, therefore, the total magnetic induction in the toroid is given by B is equal to mu n into I total current, that is mu n, that is I true current plus current due to magnetization Im, which is equal to mu n I plus mu n Im. Here mu n into I, that is mu is equal to h plus n into Im, that is M, magnetization vector. Therefore, B vector is equal to mu naught taking as common H vector plus M vector, that is the relation between B, H and M, which is this is the relation, this is the relation between B vector, H vector and M vector, relation between three magnetic vectors. So, with the help of this video lecture we understand three magnetic vectors, that is magnetic induction B vector, magnetic intensity S vector, magnetization vector M vector, and the concept of magnetic susceptibility and permeability. Magnetic susceptibility, magnetic permeability, relative permeability, and finally relation between three magnetic vectors B, S and M, that is B is equal to mu naught times of S plus M. So, the relation between B, S and M, that are the three magnetic vectors. So, with this useful and informative notes, let me wind up this session. Thank you.